Hi, this is Professor David Farina. In today's lecture, we're going to be talking about Chapter 1, the Copernican Revolution, specifically two sections, the birth of modern astronomy and the laws of planetary motion. The Copernican Revolution was a very important movement, and that movement took a very long time to start because Nicholas Copernicus wrote his book. He was actually a member of the Catholic Church, and he didn't publish it until the day he died. He was afraid to publish it because of what he already knew the church would think of this, which would be that it was heresy. And so when he died, he let this go to print, and it was not very well distributed because the church knew of it and they kind of kept things under wraps, but there was kind of like an underground, and one of those folks who received a copy was Galileo, fortunately. So I'm just going to kind of bounce through some of these slides here. They're looking a little funky. So in Copernicus's new and correct explanation for the retrograde motion of planets, you'll notice that it's kind of like when you're driving down a car, down a highway in a car. So imagine yourself, you're in a car, okay, you put your hands on the steering wheel, all right, and as you're driving down the road, you look to your left and, hey, somebody's in the passing lane and they're going to pass by you, all right, you see them pass by you, and then they get right in front of you and you end up having to pass by them. And you're like, man, this person can't drive, right? So you decide you want to get over and you're going to pass them now. So as you pass them, you see them moving backward. Now you're both moving the same direction on the highway. One person is moving more quickly. The other person is moving more slowly. And as a result, they appear to be moving backward, just like in retrograde motion. So let's describe what's happening here in a similar way. So let's look to this diagram at the bottom. You'll see here's the Earth, here's Mars, okay? Mars is going to be the slower car here. So Earth is moving a little bit faster, and as Earth moves, it goes around, and it's speeding up, and it's passing Mars right here at point, you get my mouse back here, right here at point D. You'll notice we've gone halfway around. So the motion from the Earth's perspective, there's Mars's position. By the next position B, it's here. It's moving normally from the west towards the east. But then all of a sudden it starts to move backward. As we pass Mars, because we're moving faster, it appears to be moving backward through the sky. And then all of a sudden it takes a forward motion again as we it's already in the rearview mirror now. So this made the epicycles completely unnecessary. Remember, the more simple something is, the more likely it is correct. Now, another person who picked up on these ideas was a man named Johannes Kepler. Now, Kepler was by trade a mathematician. And so he was actually working with Tycho Brahe from our previous discussion, who had these amazing tables of star locations and the precision measurements necessary to do good math with. And so Kepler was trying his best to maintain the Ptolemaic views of the perfect heavens, but he came across this idea of the Copernican model, this sun-centered model. And he really kind of racked his brain trying to figure this out, and he kept this whole perfect circular motion idea in his mind for a really, really long time. And he struggled to try to make it work and just couldn't get it to work. He also tried to get this uniform motion, once again, a first principle of the ancient Greeks, to work, and he couldn't make it work with this heliocentric model. But then he thought of something, and of course my face here is going to cover it up, so I'm going to try to turn that off for a second. And the planets move around the sun on elliptical paths with non-uniform velocities. In other words, they're making oval shapes and they're moving at different speeds. And so the resulting Kepler's laws of planetary motion were formed. The first of these Kepler's laws, the orbits of the planets are ellipses with the sun at one focus. So it's getting wonky again, I apologize. So what this means is that we've got an ellipse. Now, an ellipse, of course, is not a circle, so instead of the center of the circle, you've got something, 2 points actually, called the focus or foci. Here's one of them where the sun is. The other one is over here. And then we also have this thing called the semi-major axis. So the semi-major axis is measured from one opposite side across the center point to the location of this focus point. So the semi-major axis is a very important concept in Kepler's laws. Now you can actually make one of these if you've got a piece of string and some tacks, and you can actually draw an ellipse very easily. This would be the semi-major axis here, and then this would be the major axis. Okay, like this was the major axis. This is the semi-major axis. Now, eccentricity is a term that we use to say how circular or how oval-shaped is an oval or an ellipse. And it's calculated so that a 1 here would be a very, very, very elliptical shape, and a 0 would be a 0 would be perfectly circular. Okay, and so I've got a bunch of different eccentricity values listed for you here. You'll notice that that shape difference, and you'll notice how close the orbit of Mercury here is to a perfect circle, but it's not quite perfect. It is somewhat elliptical. And notice the sun is not in the center, it's at one focus. Now, here's the Earth's eccentricity, very small, 0.0167. Now, Pluto, a dwarf planet, has a very high eccentricity for most solar system objects, which is still only 0.248. Still almost a perfect circle. You hardly could tell unless someone told you. Kepler's second law is if you were to observe a planet in motion in its orbit, that an imaginary line connecting the sun and the planet would sweep over an equal area over an equal interval of time. In other words, A in this diagram, B in this diagram, and C in this diagram are all the exact same amount of area, but notice the different length of the orbits. This is the shortest one. This is the longest one. So when we're close to the sun, the planet has to be moving faster. And when we're farthest from the sun, the planet has to be moving most slowly. Kepler's third law is that a planet's orbital period squared is proportional to its semi-major axis, its average distance from the sun, which is represented by A cubed. Now you'll see this is in astronomical units, AUs, and period is in the units of years. So period in years squared equals semi-major axis in astronomical units cubed. And here's a graph that would show you how these two are related, and you'll see it's somewhat of an exponential relationship. And here are some of the planet's properties. You should pause the video if you want to observe these. So Galileo, he really invented our modern view of science. He used observation-based science in order to improve how we are able to interpret the world around us. This was never done before. It seems pretty practical to us today, but Galileo was the first person to truly use the scientific method in a meaningful way. He also used a telescope to do many of these observations. He did not invent the telescope. That was Hans Lippershey. But he did live at the same time as Hans Lippershey and heard about this invention of the telescope early in its use. So he was the first person to take the telescope and face it towards the sky. Prior to that, the telescope was mostly used as a military tool to view and spy on enemies, and also for a navigation tool in things like the Navy. Galileo was the first person to kind of meticulously report these telescopic observations, and he used the evidence he was able to gather to support the Copernican model of the universe. So we'll be talking about those today. The first of these, and this is a big one, he discovered that Jupiter, which we now think of as a planet, had moons. Now, here are his actual measurements that he took. So it was in January of 1610, and he saw the planet, and he saw 3 little dots that were next to it on the first night. On the next night, he noticed that they moved. Now, January 9th, he had no observations. Maybe it was a cloudy night. On January 10th, he noticed that these moons had moved again. Now, you think of this and you think, oh, well, yeah, he saw the moons. But no one ever realized that there were moons around planets. They didn't even think of them as worlds like the Earth. At the time of Galileo, the Earth was not thought of as a planet. It was just thought of the place we live. Planets were those wanderers up there, and that's all they knew of them. So this was a big deal. Now, of course, we know much more about our solar system, even just common knowledge. He also discovered the rings of Saturn, and he saw something more like this. He didn't have a clear view of perfect rings. He described Saturn as having ears. You can kind of see that. It has 2 little ear lobes on either side, right? Modern view, it looks more like this. And I will tell you from personal experience, if you ever get a chance to look at Saturn through a telescope, it is one of the most awesome things you'll ever see. I promise. He also looked at the surface features of the moon. Next time you see the moon in the sky, I want you to go outside and just take a look at it. You actually can't see that it's not a perfectly flat surface. You can see that there's slight coloration differences, but no one realized that there was actually a bumpy structure, these craters that are on the moon. With a decent binoculars, you can actually see these, by the way. You should check it out. And with a telescope, you can zoom in even more like these images. You can actually see this through a reasonably priced backyard telescope. Ask me more in class if you have questions about purchasing of telescopes. We'll be talking a little bit more as we talk through our chapter on telescopes about what telescopes are good and which ones are not good to purchase, because there are differences. And we'll talk more about that. The fact that the sun had spots on it was never known prior to Galileo. And in fact, a lot of his viewing of the sun actually damaged his eyes permanently. He went partially blind later in life as a result of his solar observations. So just so that you are aware, if you ever want to view the sun, you do need proper equipment, and I can once again help guide you towards what that looks like. Otherwise, you can use other projection techniques, but please be careful with viewing the sun. He also found that Venus goes through phases. So the phases of Venus change just like with our moon, and as a result of these phases, we were able to disprove the Ptolemaic model. In the Ptolemaic model, we have the sun, a line that goes between them, and you'll notice that if we had Venus between the sun and the earth, with the earth in the center, it would never go through phases. But yet, with the Copernican model, it does go through phases, with the sun in the center and the Earth in its own orbit around the sun.